Good afternoon, everyone, and a warm welcome to this afternoon's guest webinar from the Steel Construction Institute. My name is Nancy Badu, and I'm one of the Associate Directors here at SCI. As is usual with our webinars, you have the chance to ask questions using the Q&A panel at the bottom right-hand corner of your screen. So put your questions there when they occur to you, and when Jennifer has finished speaking, then I will moderate a question time. Handouts will be sent out after the webinar is over. Let's get started then. The topic of today's webinar is structural steel castings. Of course, these are not new. They've been used in building structures for compression members, for columns and for brackets for more than 200 years. But it's really since the 1980s that structural steel castings started to be used in offshore platforms for these huge tubular joints. I've got a picture here. The tubular joints needed in the offshore jackets to withstand the wind and the wave loading. And since then, in the 1980s and 1990s, there were further developments in the analysis and production and quality control processes in castings, and it led to more use in building type structures, perhaps for tubular joints in long spanning structures like exhibition halls or airport terminals, stadia roofs, also for bridges where fatigue was a concern, and then of course smaller castings used in facades. So this led to the SCI publication P172, written by myself, being published in 1996. Well, that's quite a while ago, and a lot has changed in the last 27 years. So I've written a new publication, which will be available and sent out to you probably end of January, February next year. Clearly, we use European standards now, so the new guide will talk about European standards. What else has changed? We live in a low carbon world, so material optimization is very important. So a good reason to use castings. Technology has advanced again in terms of casting design, analysis, and manufacturing practices. So there's a lot of interesting information to talk about structural steel castings, and I'm very pleased now to be able to hand over to our guest speaker for today's webinar, who is Jennifer Pasden. She's a licensed professional engineer and vice president of the organization Cast Connects, and she heads up their office in London. And she is now going to lead us through the webinar. Over to you, Jennifer.
Thanks very much for having me today. We're very excited to have supported the development of the new structural steel castings guide. And I'm excited to be able to today, probably to some of you, introduce the topic of structural steel castings for structural joints. And also to introduce the fact that we have just launched our first UK office. So for the first time, I'm presenting to you from London, which is quite nice to be here. And all of us, on behalf of all of us at Cast Connects, we're very excited to be working with SCI and also be able to work with our customers in Europe and other locations more closely in a more conducive time zone. So the outline of today's presentation is ambitious. I think the purpose of this presentation is sort of to whet the appetite for the fact that we have this very thorough and extensive guide coming out for the structural engineer and architects and steelwork contractors to understand how and why to utilize cast steel connections in their projects. And so I'm going to provide sort of an overview, and certainly I won't be able to cover everything in the depth that it would like, but to sort of introduce the concept and talk through some of the performance benefits, show some project case studies with the idea of just showing the range of applications for structural steel castings, and then talk a bit about when we have a custom casting, so for a project specific or bespoke project, how does that relationship work between the design team, the construction team, and what we are calling the casting supplier, the person that sits in the space that my company does, where we are responsible for the engineering design as well as the delivering and supplying the part to the project. And then very briefly touch on another sector of cast steel joints, which are standardized castings, which are products that are available off the shelf and not project specific. But before I do that, I just wanted to briefly introduce Cast Connect. So we are structural engineers who design and supply cast steel connections for buildings, bridges, and other structures. So we most of our work to date has been in North America, although we have operated globally. And we follow, chronologically follow a history of the use of structural steel castings in projects throughout Europe, China, and as well as really growing the market for them in North America and abroad. So our portfolio includes projects of all sizes across every building sector, and I really mean that when I say that. It's airport, stadia, performance venue, public schools, canopies at the entryway of drugstores, at the entryway to hospitals. And we're all very passionate about utilizing steel castings in a way that takes advantage of the values that they may offer. So we support architects, structural engineers, and steelwork contractors and other construction professionals to leverage steel castings in your work. So a lot of that work happens in what we have named complementary design exploration services. And that's just to make sure that you understand that we are here for advice and guidance without being, say, contractually engaged in order to provide that. We offer standardized products, which I'll talk about some of ours and others at the end of the presentation. So these are pre-engineered, available off the shelf. They can be specified similar to the fashion that you would specify, a high-strength bolt. Custom products, these would be for bespoke castings that are one-off. So here we're also not pre-engineering, but we're engineering, so offering design build services for these bespoke cast steel joints, as well as supply. So on to the first portion of the outline. What are structural steel castings? So normally if we were in a room together and I was able to see your faces, I would ask for a show of hands of how many people have actually worked with a structural steel casting before. I heard at some point we might have about 300 people, so I would expect there'd be a few dozen perhaps. And that's something that we're hoping to help folks change by having a presence here in the UK. But also to keep in mind, if you've ever used a tension rod connector with a clevis end, that's a steel casting. So in fact, you have probably specified and worked with them. But there's a whole host of opportunities for custom and other solutions that castings can provide. So what differentiates a steel casting from wrought steel? So many of you have probably visited a steel mill. You've seen that how a wide flange becomes a wide flange being rolled through a die down the line. But in fact, all steel is cast. So rolled steel, rolled or wrought steel, is actually poured as an ingot, or a dog bone, as it's called in the US sometimes, before it's worked and extruded through these dies to create the shapes that we're familiar to specifying in our steel design codes. So that continuous casting process is used for wrought steel shapes. The difference with a steel casting is that we're not working with extrusions. So in the picture on the right, you see we're building out a mold, we're pouring molten metal into it, and then the finished geometry of that mold is actually the geometry of the casting itself. So what that does, that is very exciting from a structural engineering perspective, is that it means that we're able to put material where we need it for the flow of forces. So we can assess members coming into a joint, and rather than being limited to cutting up, plates, angles, channels, and then bolting and welding them together, we can actually envision what would be the optimal material location to address the flow of forces through the part, and other ways that we can minimize material usage as well as simplify fabrication. From an architectural standpoint, if there are any architects, we all work with architects, they're our clients, right? It means that architects are able to sculpt structural steel. So they're able to think of this element of structure as also an element of the design. So rather than being prepared to cloak structural connections or hide them behind walls, the structural form can become part of the design expression itself. So one of the questions that we get very often, especially for those that may not be familiar with cast steel, or that may, when you hear cast, you may hear cast iron. Cast steel is not cast iron. So there are many grades that are standardized, listed in EN 10340 steel castings for structural uses that have similar mechanical properties to the wrought steel that you're accustomed to using. So something like an S355. So I just pulled out one, for example, here, G24 MN6 plus QT3. So it's a mouthful. Yield stress of 400 MPa, so that's putting it close to your S355. So the mechanicals, the weldability, the carbon equivalent, all of that that you're going to see is going to be similar for these cast steel grades, which again are all standardized in Euro codes, as well as when we work in other locations, it would be through ASTM specification. So for that reason, the first applications of steel castings that we saw in structural applications, as Nancy alluded to, would be in the offshore industry, where quite evidently the material properties of the mechanical properties of that steel that is in these ambitious structures is very important. And weldability, as you can see, the way that this node is prepared, that's quite evidently going to be welded to the attaching incoming members. You can see in the inset on the right there that this is an onshore mock-up of what will be an offshore wind turbine. And so at that red location there is where this joint lives. If there are any architects on the line, this is a beautiful looking thing, but it will spend its entire lifetime underwater. So it's not only in architecturally exposed applications where we can think of castings, they're actually very hard working. And that's why I start with this example to preclude this sort of myth that castings are brittle and that they crack and that they have poor material qualities. A properly designed and properly specified casting will have isotropic materials and can outperform material-wise wrought steel. So the offshore oil industry was using steel castings in these applications because if you think about what they're working on here, they have things like these giant towers that are holding offshore oil platforms that are constantly battened by wind and wave action. So that brings up fatigue considerations. They're also underwater in a very corrosive environment. So the amount to which they can limit the fact that the steel might start to corrode is going to be very important for a structure of this size. Having to maintain the connections is close to impossible. So the more durability that they can find there, both from the coating system and by minimizing the sort of complexity or the propensity for coating system to fail by making a much smoother joint, is going to be important. Likewise, they are in this particular application, they're looking at tube to tube connections. So if you imagine if this sketch did not have that horizontal member with its OD stepped up, you'd be looking at sort of like a starfish, right? And then you would have profile cuts of all these tubes, and then you have welds on top of welds. These are all terrible for fatigue performance. And so conventionally fabricating a connection like this, some of the things they tried were stepping up and making a through member so that you pull those weld intersections away from each other so that you just have one weld around each tube, so you're not getting weld toe overlaps. But then once the D over T ratio, or the wall thickness to the diameter of the connection becomes flimsier and softer, there is need for these internal stiffeners. It's difficult to fabricate, to stuff a plate inside of a tube and then weld it, get someone in there and hopefully not leave them there after the connection is fabricated, or grout filling, or all sorts of things. But this is basically exemplifying that it was increasing the complexity of fabrication as well as overall increasing tonnage at each one of these connections, which makes the structure more costly. Whereas turning to casting manufacturing, they're able to put molten metal where it's needed to address the flow of forces through the joint. So to give you like a sense of time, you can see kind of what this gentleman in the inset there is wearing, is that this is around the 80s when the technology advanced to the point where we could get these types of high-performing castings. Non-destructive examination techniques had advanced finite element analysis techniques. And so in the cross section there, you can see a good example of how the high connection forces, which are happening at the center of that joint, are being addressed by more material. Whereas away from those high connection forces, we can thin out to match the member wall thickness. Again, concentrating the material where we need it, and vastly simplifying fabrication. You can see there's no weld toe overlap that's going to happen at this location. And because we're moving the welds away from locations of high stress, there's again an performance in fatigue. So it didn't take long until clever engineers realized that castings could be utilized onshore as well. And some of the first examples were actually in bridges. So this is a bridge in Germany. The casting that you see in the inset in the lower right there exists at the bottom of this steel truss that supports this concrete vehicular bridge deck. So castings are ideal for fatigue, as I said, and so that's why you'll see so many examples of them being used in bridges throughout Europe. in applications where you have cyclical loading, either vehicular or rail. And the advantage that's being gained here is if we were to be subjected to local limit states that might happen at this connection point, the codes would tell you that you need to thicken the wall of the members or you need to increase the size of the members. So if you imagine much thicker or wider members here, you no longer have this sort of light lattice looking structure. And that's why in so many examples, these designers are using steel castings to lighten up the structure, to address those high connection forces just at the kernel, and then to use the members to address member forces, which is what they are intended to do. A concept that's important to understand with castings too is when we're looking at a non-standardized casting, so when we're looking at something that's bespoke, understanding that the manufacturing process requires a set of tooling to make each casting. When there is repetition, there's an economy of scale that's achieved because that cost of that initial tooling is amortized over the number of castings that you have. So something to look out for when you're assessing a project, whether it might be suitable for a casting, is there a standardized connector available off the shelf? If not, if it's custom, do I have a number of them, which will help to improve on the economy. So in this application, you can see this casting is actually identical at each one of these locations along the bottom of the bridge. Another precedent I thought I would include here, since I'm in Europe now, Centre Pompidou, these giant Gerberettes that are at the top of the building are also cast steel. Back over in Germany, Stuttgart Airport is a beautiful example of cast steel tree nodes, as we would call them. So certainly there's a more potentially structurally rational way to support a long span roof than with these beautiful trees, but it makes for a statement, it makes for a destination, and really puts this airport in the architectural canon. So at each one of these branch locations down to the trunk is a cast steel connection. Something interesting to note here is that, well, as we'll see later, castings are cast against sand, so their surface finish is a thing to consider. It can be upgraded, so it's going to come out looking sort of like an orange peel because it's cast against sand, but it can be ground and polished to be as shiny as you would like for it to be, to look even better than, say, the attached rolled steel. But you want to take into consideration a number of things, one of them being viewing distance. So this picture that we're looking at is actually taken with a zoom lens. So this is 60 feet up in the air. Only birds in the airport would actually see the casting this close. But having this picture is helpful to kind of describe this modeled surface texture that is inherent to the casting manufacturing process. Other things to consider if you're going to paint the entire thing with intumescent paint, then the surface finish of the underlying steel is really kind of becomes irrelevant because the intumescent paint tends to have a mottled texture to itself. What they've done here, which is a really beautiful accent, is incorporate these recessed reveals into the casting. So you can see with one of the incoming tubes, you can slightly see a weld mark that wasn't quite remediated. And then that's the extent of the casting. That's where the casting is welded to the tube. And then you have this recessed reveal, which draws your eye to the reveal and draws your eye to the connection point as well. So we're able to celebrate this really interesting geometry that's occurring here, very fluid, representing flow of forces and structural tectonics. But it also draws our eye away from the fact that the surface finish between the tube and the casting would be different because of the different manufacturing processes. Closer to home, so I've been enjoying taking a tour of structural steel castings throughout London in my time here. King's Cross, very notable project, utilizing again sort of a steel tree casting. Paddington Station, if you look up and if you look down and if you look up at the roof, is loaded with structural steel castings that are really nicely executed. Terminal 5, of course, massive castings supporting the structure that supports the long span roof as well as the curtain wall. So performance benefits. Why are we, although beautiful, and I've spoken about some of them, let's dial down a bit harder on exactly what the performance and construction benefits of cast steel nodes are. This is a very wordy slide, but I thought I'd include it here to be referred to again later at a later date. So overall, structural performance and efficiency is improved by this material use optimization that I've harped on a bit. Eliminating the connection local limit states, so using members for member forces, and then addressing higher forces at the joint with the casting. Reduction in member design forces, I'll show an example of that. Increasing connection stiffness and also certainty of connection stiffness. So with the casting, we're pouring one monolithic part, right? So we know what its stiffness is. Whereas there's, this, is it rigid, is it semi-rigid? When you have a bolted or welded connection is always kind of a question. Those connections can become quite soft. With a casting, we have much more certainty, which can be important in applications where stiffness is controlling the design. Improved fatigue performance, important in bridges, not so much buildings. Simplifying fabrication. So I'm going to do some project case studies, and you'll see that the connections that are there are left with very simple to access welds, eliminating the amount of cutting and amount of fitting up that's required in fabrication, simplifying field activities. So with castings, the controlled manufacturing process means that we have tolerances that are far better than those that are minimum in fabrication of connections. So that means better fit up in the field and reducing risk for all parties involved. Coating system performance and longevity. As structural engineers, we don't think about that much, but it is important to the owner. So overall installed project cost savings. And then when we have something that lasts longer and is more durable, that means that we have an overall life cycle cost that's lowered, especially when we're optimizing material usage. So that also leads to lowering the embodied carbon or carbon footprint. So then I added this, again, the main audience is structural engineers. So this isn't our ultimate concern all the time, but unmatched aesthetics. So we can achieve really beautiful architecturally exposed projects. But I also added it as sort of an afterthought, because I do want to stress that castings are used in building and bridge applications to do very hard work and improve performance, and very often no one sees them. You just may not hear about them because you can't see them. So the case study I'll show at the end of the project is a good example of that. So just as sort of a thinking model as we're going through in a minute and looking at these project case studies, if we just think about one tube-to-tube connection in this case and see what the casting is doing for us. So the overall theme is that we're moving the weld away from high connection forces. We're also reducing stress risers, geometric stress risers. So if you imagine we're asking forces to come in through that branch member and hang a right angle, that's giving us a stress concentration factor, a geometric stress riser, and that's stacked right on top of where we've created discontinuities in the weld metal. So the weld metal is always going to be the place where you have the most discontinuities and potential for failure, and it also affects fatigue. So with a casting, what we're doing is we're making that whole joint one monolithic part, and we're pulling the weld away from those high connection forces. So providing a more graceful stress trajectory and then getting the weld away from where those higher forces would be in any case. Tonnage saving. So again, using a tube as an example, although, with wide flange or channel connections, we do sometimes need to use local stiffeners. We can preclude that need with a steel casting. So addressing what would be a local limit state or a softness in a connection locally at the connection, which then allows, rather than upsizing the wall of the tube so that it can do work just at the connection point, but then be wasted throughout the length of the member, we're concentrating material where it needs to be and providing lower tonnage and lighter forces. So members connecting to castings can be designed for member forces. The other thing that's important to consider and can become really, really substantial on certain scales of project is that we are also reducing the member design force itself. So an example here is if we think about the fact that the casting is connecting away from the centroid of this connection, right? Much farther away than if there weren't that nozzle in there. That means we're reducing overall the member design force, which can, be quite substantial, especially, as I said, just depending on the geometric scale of the project. So tonnage savings can also come from in projects where we have a concern for stiffness. If stiffness or period is controlling the design, we can reduce deflections, increase stiffness, and as I mentioned before, have much more certainty about what the stiffness of that connection is, because it is one monolithic part and doesn't have these sort of vagaries with welding and bolting. Not something we think about as structural engineers, but if you are an owner or if you are a taxpayer, you are going to be concerned about the, especially for public projects, the quality of them and their durability and the expense to maintain them. So on many of the projects that we do that are outside or transit stations, it becomes very evident that having these more generous radii that do not encourage erosion and failure of coating systems, having welds that are easy to access, easy to coat, and also easy to inspect both for structural performance, but then later on for coating inspection, simplifies that process as well. So if we think back to the offshore oil structure, very important to have the coating system performance, also important onshore. So now that we've looked at some of these performance benefits to help kind of like dial down, all right, like if I'm thinking I've never used a steel casting in a project before, what are some of the top applications that we can utilize structural steel castings? Architecturally exposed, so in the US and Canada, we call this AESS, and particularly for structures comprised of circular hollow sections or even rectangular or timber. We're seeing more and more mass timber being built around the world. Timber connections are difficult. Any mass timber structure of any size is actually going to be steel timber hybrid, and because of their geometric flexibility, castings can be a really good solution for mass timber connections. Complex connections, so whether it's geometric complexity, arduous loading, again, to be able to dial down more on that connection strength or stiffness when we have a structure whose performance is going to be dictated by it. Fatigue, again, more in bridges than in buildings. And then I won't talk about this in this context, given our location, but something that we have quite a bit of experience of developing connections that are important in seismic applications where earthquakes are a concern in the region. So on to some project case studies that elucidate a number of these performance benefits in the top applications that I spoke of before. The first one, I guess I lied because this is actually a seismic application, but I will explain it quickly. Salesforce Transit Center is a 4.5 city block long transit station in downtown San Francisco. San Francisco in California on the Pacific Ring of Fire, sits on a fault line. It also sits on garbage. Basically, the soil is all fill. So all of the worst conditions that you could imagine for resisting or having a building survive a seismic event. So the conceit on this project, this is designed by Thornton Tomasetti in their LA office, was that they would use what's in our codes called an eccentric brace frame, or EBF. But conceptually, the idea is that the shear link that sits between these sort of modified braced columns, the bracing is not concentric, it's eccentric, and so it gets destroyed as the building wants to rake back and forth in a seismic event to dissipate seismic energy. In order for that to happen, it's very important that these braces and their connections don't fail first. So they are capacity designed to ensure the performance of the shear link, or to allow the shear link to actually do its work in dissipating ground motions. Also of note, these are exposed and wrap around the entire perimeter of the building. So they become the main aesthetic aspect of the building itself. And so for those reasons, the designers chose to utilize steel castings at the connection points of these large pipe sections. So you can see there's a pin at the top. The bus deck node that you see in the middle there is joining these 2-to-1 braces as they come down. And then to the base here, where we have a close viewing distance of folks that would be using the transit station. A nice close-up here. If you try to think through how that might have been fabricated, it becomes a puzzle, how this would actually be fabricated with conventional methods. And not only that, but how would it be fabricated, and then how would they cover it up? Because it would not have looked very nice. Whereas you can see in this last photo here that we've covered up the kind of bolted connection here at the ends of the tube to the plate girders, but overall, the structure is becoming part of the expression of the architecture, and the flow of forces through the structure can be seen in the joint. Another aspect of this project that that utilizes castings is something called a light column. So we'd like to think of this one as sort of a kit of parts. So it's a series of roller bent circles that are enabling this sort of opened opening up this column that sort of gradually opens up and supports an atrium that lets natural light in. Each one of the verticals is actually just a straight run of API pipe. So all of the intelligence, all of that gentle curvature is contained within the geometry of the casting itself. So with the CNC machine precision that we have in these nozzle ends, we know that as long as that pipe is straight, when it fits up with the casting, it's going to be exactly in the right place when it fits up with the next casting. You can also see in the cross section here that we are tweaking the wall thickness. So we're thinning it out to match the member wall thickness, and then thickening it in the middle here where we have these local point loads that are coming in from the rings itself. So a real expression of optimizing material usage. This project, Charlotte Douglas International Airport expansion, if you imagine sort of a cut through this cross section, there's a long span trussed roof that's supported by a vertical and a raked column. And the designers here really wanted to celebrate the structure rather than what is often the case in airports, is that these things will get hidden behind architectural metal. And so they reached out to us, and this is something that we and other casting suppliers can do with clients, is take a look at, okay, what are the geometries? You have a vertical column and you have a raked column. What is the outer diameter that you're getting to with your design at this point? And then we start to think about what it could look like and also how it's going to be constructed. So in this sort of design exploration process that you can see here, we were entertaining the idea of maybe having a pin connection, which we thought would be potentially helpful for field direction. But where we ended up with them was actually they wanted something that was very smooth, so that there would be less likelihood of people banging into it and having its coating system chip off. So it would have less corners to collect dust and dirt and detritus. And then also they wanted to not intumescent coat the base of this casting. And so we had a clever way around that, working with the fire protection engineer. But I'll just show you, this is an example I like to show from JFK Airport of this is the reality of your life as a structural connection in an airport, is that people are going to bang against you, they're going to drop dust on you, and no one ever includes in the maintenance plan how do we upkeep this connection. So this is not the oldest terminal, and you can see that this has been through quite a bit of wear, and also features a lot of sharp edges and layers and things like that. So having a more smooth connection geometry here was the goal. And then also to preclude the need for intumescent paint, because the casting is hollow, we're able to grout fill it for some of that fire resistance. And we were also able to easily tweak the wall thickness of the casting so that at elevated temperatures, the design capacity ratio in the casting would be such that we wouldn't be worried about a failure. So you can see these castings in the wild here and how nicely they have turned out. That is a custom casting. Also featured in this is a standardized casting. It's a taper in a pin connection, which I'll talk about briefly at the end. Mass timber is another top application. So here we have these glulam trees that at each connection point have either a standardized or a custom designed stainless steel casting. So we can cast in carbon steel, we can cast in stainless steel. In this case, stainless was chosen because they didn't want to paint the steel, and also this is a bit of a humid environment, so they wanted that protection. In New York City, a stadia, Arthur Ashe Stadium, this is actually another seismic application. So if you see these mega columns at the base, the whole thing is meant to work as a specially detailed concentric brace frame, which has certain requirements for detailing such that this gusset plate can hinge out of plane to allow those braces to be dissipating seismic energy in the event of an earthquake. So the extent of the casting is shown in this render here, and it's just welded to the tube into the base plate. And just to give you a sense of what maybe a fabricated alternative for that might have looked like, the gusset plates on these SCBFs get very big. This is not actually an SCBF, but anytime you have a gusset plate to a column connection, we see this a lot in stadia. You have, gusset plates that are like the size of the concession stand back here, whereas here we have a much more compact, high-performing, and lighter connection solution through a casting. We sometimes work on art projects. So this is actually, it is a structure, but it's a permanent art installation. This is another example I wanted to show because it is super duplex stainless. So these joints at the top of the roof here are cast in super duplex stainless equivalent grade, and they're allowing the slenderness of the structure. So it's meant to be very ephemeral looking. It almost looks like it wouldn't work, but that's because all of the moment that is happening here is happening through a casting that gets very, very thick. If you were to try to execute these connections with fabrication, the members themselves would have been quite a bit thicker and bulkier. This project with Roger Sturckarber and WSP and Eckersley O'Callaghan in World Trade Center 3. This is actually the lobby of World Trade Center 3, where the designers wanted to use this sort of, this is their drawing, this articulated pin connection, and building it up out of plate turned out to be, I think, quite costly, but we were quite easily able to cast it. And it just really shows the creativity that's allowed when understanding casting manufacturing, what we can do to, the lowly pin connection to make it be a really interesting part of the design. This is another standardized product application. So this time a commercial application. We just have universal pin connectors, or UPCs, at the ends of these raked columns, that 60-foot tall columns that support this bustle of commercial space, as well as in the vertical bracing at the top. For sense of scale, that's a 610, so 24-inch OD, or 610 millimeters. This is a project with SOM, again, utilizing a standardized pin connector as well as a custom V-base at the bottom. This is for a university application. All right, so now into the sort of meaty part. Now that we've seen some examples of both projects that utilize standardized pre-engineered steel castings and some that use custom castings, let's dig in a little bit further into the project delivery process for custom steel castings. So first, starting with who is this casting supplier and what is their job? So the casting supplier's scope of work, I like to include the pre-tender. So before the project goes to bid or to tender, in order to assist the specifiers, a design team, structural engineer, and architect, in assessing whether or not a casting is a good fit for their project, there is the opportunity for the casting supplier to provide conceptual design and budgetary estimating. So if you think back to the Charlotte Douglas Airport casting that I showed, we have these various different design iterations. That was a process of thinking through constructability and also aesthetics for the designers, thinking through how we incorporated that fire resistance, and then also providing them with budget estimates so that they could ensure that that would fit within their project. So that's an important step for custom castings because they are project specific. There's not a list price as opposed to, say, a standardized casting, which would have a list price. So many casting designers will work through this process with you, again, without being contracted, with the eventual idea that hopefully they will be able to bid the project when it does go to tender. So When the project goes to tender, the casting supplier will provide their quotation for the custom casting to the steelwork contractor. Sorry, I left fabricator. That's what we say in US. The steelwork contractor, who essentially eventually would be the person under which the entity under which the steel casting supplier would be contracted. So the scope in more vague, I'll get more descriptive, but is to design, detail, and engineer the castings. That includes establishing interior and exterior dimensions, so drawings, and the preparation of a casting production specification, which includes material selection, NDE examination requirements, and all production parameters for the casting. So that is a very thick spec and very technical, but essentially the message I'm trying to give is that the casting supplier is responsible for delivering to the project steel castings that meet the performance needs that are specified by the design team. And then the casting supplier in this role also would be overseeing the manufacturing of castings, making sure that that production specification that they provided is met, and then ultimately supplying them to the steel fabricator. So in the guide, to help kind of clarify some of this process, we have some visual aids and things like that that I'll give a sneak preview of. So this is trying to describe the sort of contractual relationship. So the hard line is contract. So the casting supplier works under the steelwork contractor. Foundries are the people that make steel castings. So in the way that we operate, we subcontract that manufacturing to the foundry, but we take responsibility for every element of it and make it very clear to them what we're expecting from them, and the non-destructive testing and destructive testing, and all the submittals that they need to provide to us to ensure that they're meeting the production specification that we have written to meet the performance specification, which comes from these bodies, structural engineer, architect, and to some extent our customer as well, the steelwork contractor. So we go into more depth in this in the guide again, but just to kind of let you know that that is going to happen, and that you probably want to spend more time with it outside of this presentation if you're interested in specifying a custom casting. There are three kind of main communication or submittal documents: the performance specification, which I alluded to before. So this is given to the casting supplier by the design team. Casting design report, this is going to contain all of the evidence of all the engineering assumptions, the geometry of the casting itself, any FEA that was conducted for the custom casting, all of the assumptions that go into the FEA, and also proof of concept. So the FEA results, how we interpret them, how they are then linked with the performance that's been required by the structural engineer, is all very clearly described, pictorially, tabulated. All calculations are listed. So it's a very thorough report. In the sense, the way to think about it, I guess, is as the casting supplier, we are the casting engineer and taking responsibility for that, but we need to prove to the structural engineer that we are providing them with something that will meet their project requirements. In order to do that, the casting supplier is writing a production specification, which goes to the foundry, which is detailing, as I said before, all the requirements for what is the alloy, what is the method for verifying mechanical properties, what are the required submittals, and some things that I'll talk about a bit more in the example. I probably won't spend as much time on this as I thought I might, but so again, this performance specification is outlined inside of the guide, and is it's essentially architectural and structural performance requirements developed by the designers and given to the casting supplier. I should say that this would occur at the point after the when the job is going to tender. In order to quote or bid on the custom steel casting, the casting supplier needs to have this information so that they can develop the quotation in a way that will ensure that it will meet the performance requirements. So this is happening at tender, and this information would be included both in drawings, detailing where is the casting, what is it connecting to, is it part of a lateral force resisting system? What are the loads that it will be seeing during its lifetime? What is it coated with? All these things, and also included inside of the specification language at tender. Casting design report is developed once the job has been tendered, the steelwork contractor has been awarded, and they award a contract to the casting supplier. This is when the engineering work that will ultimately be all reported inside of this casting design report is commenced upon by the casting supplier. They will supply this to the design team through the customer before commencing with manufacturing of the casting. So this is a submittal that needs to be approved. It needs to be discussed and coordinated, and we need to make sure we're all on the same page until we would go forth and start to make the casting. Right, so some examples, we'd be including mesh densities, mesh types, sensitivity analysis, post-processing of FEA results. Also, in any custom casting, typically there are locations where we can use codified equations. So those hand calculations would be given in. It's the locations where we're not following beam theory, where we have disturbed regions that we need to be using finite element analysis, that we need to make clear all of our assumptions in our process through that. And then, as I said before, ultimately these shop drawings are developed as cast and machine shop drawings. Those are also communicated to the foundry because they are the ones that are going to be constructing the molds to create this as cast geometry. And that is part of the production specification, the shop drawings, as well as the requirements for production. What is the BSEN 10340 grade that you are using? What are the other standards that are referenced for non-destructive testing, destructive testing, and at what frequency and in what method are these things reported? Rectification of defects, I'll talk about that briefly when I use this case study to hopefully help to give an example of how not only are the performance benefits of castings leveraged in this project, but also how does that sort of flow of information transfer work on a custom casting project where we have the casting supplier taking responsibility for the design and supply of the cast steel connections. So this project is MSG Sphere in Las Vegas. You may have heard some things about it on social media. It is the largest spherical structure in the world, 560-foot diameter. The large spherical structure portion is actually the red part that you see here, which encloses this dome roof, which is actually the performance venue. So tucked inside of the exosphere is the performance venue. And tucked inside of the performance venue is a spheroidal grid shell that is hung from the dome roof. I won't be able to talk about that today, unfortunately, but that's what you've been seeing on social media. If you don't see the outside, you're seeing the inside, the U2 concert and all of the amazingness that's happening here. Too bad I can't talk about it. There were hundreds of connections in that structure that enable it to have the tolerances that were required in order to make a never before seen LED screen. And there's speakers and they blow air on you and there's smells. I don't know, it's a whole thing. So unfortunately we can't see the castings, but what they enabled is pretty impressive. But what I'll talk about more here is this red exosphere. So this is what makes it the largest spherical structure in the world. So it's essentially, it's like a modified geodesic dome. So some of the rules were broken for the buckyball at the top in order to make the connections more feasible. And also important to note that all of the pipe here that is connecting to the castings is just straight runs of pipe. So this consists of straight runs of pipe, and the castings are doing all the work from a geometric standpoint, which again, we're taking advantage of the controlled and tighter tolerances that are achievable and consistent with steel castings. In a grid shell, if you have tolerance stack is a real concern. So if we look at the initial options that were explored by the design team, there included 2 fabricated options. And then there was this concept of perhaps using a cast node. So this was all before tender. And again, in this application, we had the opportunity to work with the structural engineer of record, the owner, and the pre-construction steelwork contractor to help them explore more thoroughly the realities of what the casting would be offering, and also to draw to light some of the sort of shortcomings that would have been with this fabricated concept. So what you're seeing on the image right now is at scale, an example of one of the cast steel nodes in this project. So you can see the casting is much smaller, it's much lighter, and it is much less complex. So something that was kind of missed, I think, in the original concept was that these castings, because the connections themselves are connecting to straight runs of pipe, that means that their arms have to be canted slightly in each direction and very exactly, or that tolerance stack becomes a project killer. And so to take these plates and weld them slightly canted would have been very problematic because there's always distortion happening when we have welds. So to think that all 6 of these arms wouldn't be slightly different and off in one different way was probably a pipe dream. Whereas with the casting, each one of these touch points that you see this red here is where the flange plate end of the pipe member is going to fit up with the casting. CNC machined and exact, and I'll show you later, it's all scanned and whatnot to ensure that they're exactly in the correct place. So this was an infographic that we put together to help explain some of the advantages of this cast node option. So we can see 1/4 of the weight, and the kind of, this is not the most complex joint on the project. So up here we probably would have been at even like a fifth of the weight. Far fewer bolts, so timing construction is important. So the amount of time it takes for a person to tighten a bolt is something to consider. Coating system, again, I harped on how we don't think about that all that much as engineers, but it is important. And precision, again, with this CNC milling. And also all of our price for all of the quality control and non-destructive examination was included as it was compared against this fabricated node option. So a lot more certainty and a lot more control up front, a lot of risk reduction, which is very compelling to all parties involved in the project. So what happens next? So once the steelwork contractor provides a contract to the casting supplier, there's that communication flow. So the engineer, the structural engineer, needs to provide center lines and member sizes, the geometry, and then also the loading on the casting itself. So that would be part of what they're communicating in the performance specification. Then begins the casting supplier scope of work, which also is eventually going into this deliverable that will be the casting design report. So there's the finite element analysis, modeling, post-processing, and putting that all in together into a package that is easily understood by the structural engineer and ensures that we have coordinated and that we're meeting all the production performance requirements of the project. Something to take note of in this level of FEA that we're doing is that we have to be very savvy about, yes, there are locations of this part like the tubular members that can be done as beam elements and perhaps the flange plate, but this was a good example where we realized that actually this type of flange plate connection, the equation for prying, at least in the American codes, doesn't actually really apply to this certain the way that this geometry or this connection is actually detailed. And so recognizing that, we were able to do nonlinear analysis and to really dig in on what's happening there when that prying starts to happen, to make sure that globally it was not going to be a problem for the overall structure, and also, of course, so that you weren't going to have problems with the connection strength itself. So that's something that, digging down with this finite element analysis allows us to do, which is not your everyday connection design, of course, when we have more general codified equation designs. I mentioned a few times about strength and stiffness being important. So it's important for us when we are working with a structural engineer that we can ensure that whatever they have included in their global structural model, their assumptions, that we are meeting or exceeding them when it comes to strength and stiffness. So this was a check that we did on that. The engineer had modeled things as sort of just centerline to centerline tubes. So the casting does prove to be stiffer than a tube centerline to centerline tube connection, but it's something that we want to coordinate and make sure of on all projects. So through all this engineering work, developing the designs, another deliverable is the as cast and machining shop drawings. And now very quickly, a little bit about how we actually manufacture the casting. So castings are cast against sand. In order to make that sand mold, we first create tooling out of timber. So CNC milled timber tooling. That tooling is basically the negative and the positive of the part. And so we're surrounding it with chemically treated sand that sets up and has a binder and becomes very hard very quickly. And that will ultimately be what the molten metal is poured against. So here you're seeing the actual sand molds. The entire thing is enclosed in a steel box, basically to counteract the fluid pressure of the molten steel as it's poured into the mold. And in situ, each time we're doing a pour from one of these ladles, they are doing spectrochemical analysis to check the alloy, and also pouring keel blocks either attached to or pour bars separate. And each one of the destructive examination or non-destructive examination tests that happen along the lifetime of this casting production is tied to the serial number of that unique casting. So there's traceability back to the pour and back to all the testing results. Skipping up quite a few steps, it's poured and it sits for quite some time. The binder decays and the sand falls away from the casting. These appurtenants that you see here are a key part of the casting manufacturing, which is ensuring that when this steel starts to solidify, that it is solidifying from one side to the other. So that directional solidification means that we have the grain structure continuity inside of the part, which allows us to say that it is isotropic. With rolled steel continuing casting process, you have problems in plates, for example, with centerline shrink. So you have steel cooling from the outside in, and you can get these centerline shrinkage, which is why we know we don't load plates perpendicular to the direction of rolling, whereas with castings, we actually have the isotropic material through this directional solidification. So these elements are removed, they're cut off. In this was a quench and temper grade. And that's right, I wanted to show this. You can see that there's a keel block that's been poured alongside this part, so that will be destroyed with various types of testing so that we can confirm the mechanicals on that part. And then NDT. So there's a suite of non-destructive testing. Some of these are in 1090 Part 2 are actually described. A qualified casting manufacturer might even want to exceed the expectations of 1090.2 or an ASTM equivalent. And so it's important that in that production specification, the casting supplier has provided not only the suite of tests, but the frequency as well as the acceptance criteria using these standards that are relevant to the authority having jurisdiction. Something interesting about steel castings is that always in the production of a casting, when it is cast, the non-destructive examination will be performed, and they will always find pieces of it that don't meet the acceptance criteria. That is expected. It's part of the whole process. So they have something variously called weld repair or production welding because it's part of the production. That piece, the little rotten piece, is arc gouge weld repaired. So it's removed, it's filled with the weld. The testing is reperformed. So we go through this process until everything meets the acceptance criteria. And then finally, because it's been welded, there's a heat treatment for residual stresses. I'm going to skip through some of these, but photometric survey is utilized to confirm geometries, as well as balancing the part so that when it goes into the machining jig, we know that those that the nozzle ends, the faces, and in this case, the bolt holes are going to be exactly in the location that they need to be, so that when they get into the shop and they get into the field, everything is going together, and we're keeping the tolerances as tight as possible to enable the construction. Finally, after machining, there's a robot arm that surveys every node that's overlaid with the model, and all these reports are provided to ensure that. We're often thinking about how we can help fabrication and erection. So this is beyond the sort of structural performance or architectural performance requirements, but when you are dealing with really heavy pieces of steel, it's really nice to just be able to look at them and know that this way is up. So this is what this arrow is telling us. There's also clocking marks and metronomy survey marks so that when they're in the field, they know that they have the tubes in the right place clocked to them, and that they're able to shoot these things and in surveying them, especially in an area where temperature change is significant. So finally packed up for shipment, and it's always good when you see an erector on the first try smiling like this when the piece all fits together. And the proof in the pudding was that the top came in and fit. And this is my favorite thing I've seen on social media, because they actually did a rendering in the outside of the structure that is underneath that you can't see because of the LED screen. All right, the last thing that I don't have too much time, so I'm going to go through this really quickly because I do want to allow time for questions, but maybe suffice it to say in this section, I was going to speak a little bit more about standardized pre-engineered castings that are available off the shelf. I'll just show you very quickly some examples. We saw some examples of this used in a project. It's a Clevis connector for hollow structural sections. And this is one of those examples where if you need 2 of these, it's just as good as if you need 40, because we have them available off the shelf. So there's that economy of scale that you can take advantage of. From small to large sizes available off the shelf. This is a fabricated pin down the street from me here that I've been scratching my head around. So, there can be complex fabrication to achieve a pin connection. It's much simpler if you can buy the thing off the shelf, and then, precluding all this profile cutting, and that becomes very costly and hard to control from a tolerance perspective. With a standardized casting like this, you just have one downhand weld that goes around the collar of the casting. So a real risk reduction for the steelwork contractor if they're able to just purchase this product and plug and play. Some examples of applications: the Whitney Museum, high profile, high budget, but also a public school, a public school library in Ontario utilizes that exact same pin connector that Renzo Piano Building Workshop utilized. One more, Diablo bolted splice connection. So with all these standardized cast steel connections, what we're trying to do is eliminate field welding and eliminate if possible shop welding as well. So this is a field bolted splice connection that allows you to have this concealed connection for circular hollow sections. Specifying standardized castings is a much easier process than the custom casting process. Most manufacturers will have technical data sheets, relevant geometries. They'll have 2D and 3D details for you. They'll have Revit, SDS2, and Tekla. So it's really just dropping in these assets into your design drawings, as well as spec language. And with that, I will curtail and just come back to this, outline that we have for the structural steel castings guide, and I'll turn it over to Nancy to see if we have any questions that came in.
Thank you very much, Jennifer. That was a really interesting presentation. You covered a huge amount in just 50 minutes. Yes, there are a few questions, if you don't mind. And the first one is about connection stiffness. And obviously, a very important point. How would you go about estimating the connection stiffness for a cast steel connection?
There's a few ways of answering that, I guess. So it's not really an estimate. So once we built a three-dimensional model of the casting, we know its stiffness. We know the material stiffness and we know the geometry of the part. So if it's the question is in design, perhaps if you're putting together, say, your global model and wondering what kind of stiffness you should have in your connection points in your model, that would be an opportunity to have a conversation with a casting supplier who could, build out a design model for you and give you that stiffness. The other way to answer it is it's between rigid and centerline to centerline model, right? So it's not completely rigid, most likely, unless it's a solid casting, and in some application you might have that. But it's going to be stiffer than if the members were modeled to just continue into the joint.
Thank you. Let's move on now to questions about ductility and toughness. Are there any particular requirements for ductility of castings? I mean, we're very familiar with the Eurocode ecosystem when it comes to fracture toughness, say in Eurocode 3 part 1.10. But tell us what you can about ductility and toughness.
Sure. Yeah. So I think so that is a performance requirement. So whatever ductility or toughness is required for the project by the structural engineer would be the ductility and toughness that the casting supplier would need to ensure is delivered. So when that is related in the performance specification, then the alloy would be chosen to meet those requirements.
Let's switch now to software. What software is used for a typical finite element analysis?
There's a lot of different ones. We use HyperWorks, which is an Altair product. There are, that's the only one that I can vet, has all the bells and whistles that are needed. But what you're not going to use is like SAP or ETABS, which are component-based finite element analyses, right? So we don't need all the bells and whistles of replicate the floor and make me a beam or a column element, because we're using first principles when we're doing this disturbed region finite element analysis.
Thank you. Now, moving to manufacture, how long does it take to manufacture a casting? For example, a node with 4 incoming members.
That's a very good question. Thank you. That is something that I glossed over. Part of the performance specification and understanding that needs to be communicated at tender, of course, is what is the project schedule. So even before that would happen, that's one of the things that we would do if you reach out to us, is give you an estimate for how long it's going to take to deliver the casting. Because if you have a very fast track project, then it may not be suitable. So standardized castings are available off the shelf. So it's just the time that it takes to take them off the shelf, blast them and pack them up and ship them to you. So the order of, we would typically say 8 to 12 weeks, although, special expedited shipping can be arranged for those standardized castings. However, looking at project delivery timelines, 12 weeks is not going to be holding you up. It's going to take the steelwork contractor that long to get their stuff from the mill. With custom castings, there's a longer lead time because of what we saw in that there's the engineering process, there's also the building of the tooling, and then there's all this very extensive non-destructive examination that is specific to the project process. Something I didn't quite touch on is that there's always one of the custom castings made first, the first article, that is inspected a lot more than the rest of them, right? So that's to approve the process. So because of that staging and all the work that goes in up front, before we can churn out the castings of a similar geometry, then lead time, I hesitate to say it because it seems like a very non-specific answer, but between 22 and 30 weeks, and that will depend on the size of the casting and the complexity of it, and to some extent understanding the way that foundries work. If you can fit into their schedule a little bit later, they might be able to do it faster, but if you're asking them to do something very quickly, it could be sooner. But maybe the takeaway is that that would be very clearly communicated in the quotation that's provided to the steelwork contractor, so that we're all on the same page about what the schedule would be for delivery.
Okay, thank you. Are there any rough criteria for determining whether a cast connection is viable compared to a fabricated connection?
Yeah, that was kind of the slide that I have that are performance benefits of steel castings. If you have a complex fabrication, so if there is a lot of cutting and millimeters of weld, length of weld, if there is a requirement for weld remediation, so if it's a project that has architectural concerns that ask for blending and grinding, those are time consuming, right? So the expense in fabrication comes from labor more than material these days. If you have a connection that would require a lot of field welding, then certainly savings are going to be had if you can preclude that field welding. Those are some examples, but yeah, the arduous loading, complex geometry, if there is high repetition, again, because, with the casting,
Yeah.
once we go through that process with one of them, we can churn out identical ones like widgets.
Right. Now, I've got a question here about additive manufacturing. What part does additive manufacturing play in developing castings?
Well, there is a capability to 3D print the sand molds, although that is not possessed by every foundry. It's not something that they've adopted very much, although there is a possibility there, which could mean faster production time of the sand mold. People will also often ask, why aren't you just 3D printing the metal? But the technology and the standards are not quite aligned for that yet. It's certainly possible. It's something that we've been looking at with a 3D metal printer in the US. So there is certainly an application where perhaps we have a cast steel node and there's 20 of them, they're identical, except for 2 of them have this appurtenance or something that's slightly different. Can we then use additive to print on that portion? We absolutely could.
Thank you. Gosh, I think we're going to have to stop before we've answered all the questions, but let's just do a few quick fire questions. How small can you cast a node, say, for connecting tubular members?
Yeah, it depends on well, as small as you like, let's put it that way. But if it is meant to be, say, like the example I used, the field bolted connection, then you have to take into consideration whether or not you can fit the bolts inside. So the smallest that we've made is 5 inches, which I won't be able to rattle off the millimeters for that yet. But that was just a matter of fitting 4 bolts into a cruciform. And that also, I think, goes back to the question about when should you consider a cast steel joint. So small, they can be quite small, but you just have to think about the way, like mechanically or chemically, is it going to be connected to the member. Also, in facades, you see a lot of really small castings as well. So they can go down to quite tiny. And size-wise, with respect to the other end of the spectrum, some of those examples I showed from the offshore oil world show you that they can be really, really quite big.
Yeah, of course. Well, someone's asking whether cast elements can be fabricated in the UK. Of course they can. There are many great foundries in the UK.
Yes.
That say fabricated the Heathrow castings, other castings. So just look at the Trade Association to look up the foundries. What else have we got? Are there any load tables for standardized castings? Well, again, you'd want to go for the product manufacturer. There probably are load tables for castings, for example, by McAloy. Geometric constraints. Well, we've touched on size. What are the other geometrical constraints? What can't you cast?
I would say one geometrical consideration is if you have something that looks like a wide flange, like an extrusion, it should be a wide flange. It should be wrought steel, right? We don't want to try and cast a long extrusion or cast a long pipe. You know, maybe we would cast a tapered pipe. We do actually have a product that is off the shelf that's a cast steel taper, but if the cast steel taper becomes 25 feet long, you probably want to look at doing that in a different fashion. A lot of the examples I showed you are very smooth geometrical transitions, which is driven in part by the fact that that's the way that forces flow through a joint most efficiently. We can't cast a knife edge. We can machine a knife edge into a casting, but that's just kind of getting into the weeds. But
yeah. Okay, and now last question is about welding. Anything special when you're welding a casting to a hot rolled section?
So what cast steel grades have very similar and dare say equivalent weldability CEV values to the wrought steel grades that we're customarily using in construction. The base metal is going to match most often the wrought steel that's being attached. So in some depending on which codes you're working in or what the AHJ is or what the sector is, you may need to develop either a more thorough welding procedure specification, depending on what the joint types are and whatnot. But I think the process itself is straightforward. It's more that the procedures may need to be qualified depending on who the regulator is.
We hope you found the webinar interesting, useful. Well, I'm sure you have. Perhaps you should consider becoming an SCI member if you're not one, and then you would be able to come along to our SCI member only webinars, which start again next year on the 9th of January. So just leaves me to say thank you very much, Jennifer. Thank you for listening, and goodbye.